Hey there, friends and neighbors. Can we talk a little MPLS? In this video, we'll talk about some of the ideas and the RFCs behind this multi-protocol label switching. Well, to sort of understand where MPLS comes from, or at least the motivation behind it, we have to sort of remember that the internet is ever growing today. I mean, if you just think about the number of people and the content that we push on there. But the internet, when it first started, was nowhere near the size that it is now. But with new applications, more users, more networks connecting, interconnections between internets, and more demand for content and everything else, the internet has just exploded in growth. Well, what does that mean? Well, it means that everybody wants more capacity, more bandwidth, more speed. We have the desire to connect via different technologies, cellular, 802.11. And then sometimes we want to provide different classes of service to different kinds of applications. And so that becomes really, really important. And then we can also implement ways to manage all of this traffic as it moves through the network. So if you're trying to figure out how to handle all of this growth, and you're trying to figure out how to manage all this data and all of this traffic, well, maybe MPLS can have some of the answers. Let's take a quick look at core routing table growth in the routers. So this is a graphic that appears at bgp.potaroo.net. You can go out there and take a look at it yourself. So what we're looking at here on the y-axis is core router routing table size. And so that top value is 900,000 routes. Now, just a couple of years ago, right, if we go back to, 2013 or so, we're coming up on 500,000 routes in the core routers. And now we're coming up on 1 million. That is a lot of routing table entries. So routers are just computers, right? They have a certain ability to process a certain number of packets per second, and they have a certain amount of memory associated with them. Well, this is one of the aspects of that explosive growth that we were just talking about. It's not just that people want to connect. It's not just that they want access to data. It's that we've got so many endpoints and so many users that we got to figure out how to route all that stuff. And that results in massive explosion of routing table size. Hardware switching at layer 2 is really, really fast. So within a network, you have switches that really just have to do an error check on the CRC and then process the source address table, and then off it goes. But at layer 3, we have to hit a router, and now we got to process the IP header, and that includes the header checksum. We've got to figure out the source and destination IP address, so it's additional processing. So routers are always slower than switches. But what if there was a way to sort of take advantage of the switching speed by not really processing all the layer 3 header for each and every packet for each and every hop? Then we might actually get a performance benefit. So the way that it works is you do the routing decision once on the entrance to this thing called the cloud. And then all of the other decisions are made at this thing called a label that sits at layer 2.5. Now we'll be really clear on that here, what that means in a little bit. And so that means you don't have to make all those routing decisions. And then when you get to the edge of the cloud, you make another routing decision, and that's it. And so that's one of the ways that MPLS moves away from the traditional model of straight up switching at layer 2, routing at layer 3 to do something just a little bit faster. So how do routers normally forward? Well, when you think about a routing table, right, you've got a destination network, you've got an interface that you use, and then you've got the next hop. And every packet is processed in that way. So you hit the routing table, the router figures out what to do with the packet, and then it sends it off to the forwarding router. And that's the way that we handle things normally. That's normally the way that we think of processing IP packets. Now, IP packets just have the source and destination IP address, right? So every router has to figure out what the next hop is, and then eventually the packet finds its way to the destination. And then an important idea is this idea of return path, which may or may not be the same pathway in reverse as the forward path. So there's no guarantee that packets follow the same pathway out and then back. But the same idea is true. You've got to figure out the next hop, and then the next hop, and the next hop, and then finally get it to the destination. So MPLS sits in between layer 2 and layer 3. So it operates over whatever layer 2 technology you have, and then right in between there, right before you get to layer 3, what we're going to do is stick in an MPLS header that includes, among other things, this idea of a label. So what we're going to do now is we're going to map destination networks to MPLS labels. And when we hit MPLS enabled devices, we go up and we process the layer 2, then we process the layer 2.5, and then we don't have to do the layer 3 header. We forward things just based on labels. I would be remiss if I didn't say that MPLS was not aware of flows and uses something called the forward equivalence class to handle flows of a particular type. So what's a label? Well, I've mentioned this a couple of times, right? What we're going to do is right above layer 2 and right below layer 3, we're going to squish in this shim. And the shim is the MPLS header. And one of the things in the MPLS header is the tag. And the tag is going to be used to forward traffic instead of the layer 3 header. So the header includes one or more tags, and that constitutes what we call the label stack. And then we've got some other detail in there, like the time to live, like the forward equivalence class, like whether or not it's the last tag in the stack. And that right there constitutes the MPLS header. Well, to begin at the beginning. Back in 1997, there was this thing that Cisco put out called the tag switching architecture. And it was this brandy new idea on how to forward packets. So the fun part about this RFC is that it's not really an RFC like we've come to think of them. And here's a quote from the beginning of it, right? This protocol is not the product of an IETF working group, nor is it a standards track document. This document provides an overview of a novel approach to network layer packet forwarding called tag switching. So I'll remind you of the growth, the bandwidth demand, the multimedia applications, the growth in the routing tables, and all of those things that were creating problems. And so that was sort of the motivation, the impetus behind this tag switching architecture. So the components of tag switching include the tags and everything that we've talked about so far, but there's a big difference. So what MPLS does is it does exact match forwarding, which means it tries to find the exact tag to match it to the network destination. This is as opposed to routing IP packets. And remember that the big three when you're routing packets are prefix length, administrative distance, and metric. Prefix length is longest match. And so what we're after there is the longest prefix match, or longest prefix length that matches a destination. And so it takes a little bit of time. When you're doing just the exact match forwarding, finding the tag that you need and sending it off, you get this increase in performance. MPLS came a little bit after tag switching, just a couple of years, and it has its obvious roots in Cisco tag switching. And then a couple of other companies joined Cisco in this effort to create something that was the actual IETF standard. So there's a checklist of MPLS design requirements. You can probably imagine what a lot of them might be. If you're going to put this thing in the internet, or you're going to put it in provider networks, then it's got to be backward compatible. It can't change things a whole lot, other than to say, if you have an MPLS enabled device, you're going to add this shim and then you're going to act on the shim. So got to work with most technologies, because remember, it sits above layer 2. It's got to be compatible with network layer routing protocols. When we get through some of these videos, we're going to see that we deploy MPLS on an OSPF network. It doesn't have anything to do with the routing protocol itself. It's deployed along with the routing protocol. And then you've got the flows and the different quality of service concerns. And so it's got to have this ability to handle what we call forward equivalence classes. You don't want to get into loop problems. You want to be able to manage a hierarchical structure. The internet is in many cases a hierarchical structure. So we want to retain that. And then it should be scalable. You don't want something that you're going to put in place that doesn't grow along with the internet. So this is some of the language associated with MPLS, right? An elegant solution that handles all of the problems that we've been talking about that came from the explosive growth. There are a couple things that MPLS doesn't do. It's not a jitter, delay, or congestion solver. It does have a quality of service, or at least forward equivalence class mechanism. As far as the topic goes, MPLS might have the highest number of related RFCs of any other topic. There are really just an enormous number of ideas associated with MPLS. It is designed to be an open standard, so there's lots of ability to add to the protocol or make some modifications or improvements. Now, a key idea is not just that we're going to stick this label in there and then do forwarding based on that, but we've got to find some way to get the labels distributed to the different routers. So another part of the MPLS architecture is something called label distribution. So there are tons of RFCs. We're just going to talk about a couple of them. So RFC 3031 is the architecture, and you can see that this particular RFC is updated by a couple of more. The label stack encoding that describes how that is built. So that image there in the middle of the screen showing the label and the EXP and the TTL, that is from the original label stack encoding. And you can see that there's a whole bunch of RFCs that updated this one. And then, of course, another one that's important to us, at least for this set of videos, is RFC 5036 that has the LDP specification, and that obsoletes 3036. Now, in previous videos, we talked about differentiated services. And so what if there was some kind of cool way to create yet another mapping between class of service, DSCP bits, and the flow classification for the MPLS traffic? Well, RFC 5462 does just that. Multi-protocol label switching, support for diffserv. So I'll just read the quote here. The format of an MPLS stack entry is defined by 3032, we saw that in the previous slide, to include a 3-bit field called the EXP field. Now the EXP field, or experimental field, was never really designed to be experimental. It was always designed to be some kind of class of service. And so what 5462 does is says, listen, it was designed to be class of service anyway, let's just make those 3 bits class of service. So you see the TC bits down there, that's the traffic class field. And of course, it's 3 bits. That should be, if you watch the other videos, you know where those 3 bits probably come from. So again, here's our current MPLS label and just a little more detail about each one of them. So the labels are the actual values. Now the label field there looks pretty big. You'll see that a lot of the labels that come out have actually small numbers associated with them, but we need room for something called the label stack. We've got the class of service. We already talked about that. The bottom of the stack is a significant bit, because what that tells you is that if there's more than one label, so you put together a collection of labels that constitute a path, as you go from hop to hop, the labels are removed. And the last label in the stack is called, or the last label in the header is called the bottom of the stack. And so this is an indication of whether or not you've reached that. And then, of course, we got a time to live. Couple of details about MPLS labels. They only have local significance. And what that means is that they can be end-to-end, but they have to be mapped end-to-end. To begin with, they only have local significance. So what happens in a router that's performing MPLS forwarding is that a label is input to a particular port, and then the router creates a mapping from that label to a different label on the outgoing port. There's nothing at all that says that a label's got to be there across the entire MPLS cloud or topology. Now, it certainly could be the case that you map them continuously, but it's not anywhere near a requirement. Now, the pathway that an MPLS labeled datagram takes through the network is called the label switched path. And this is very similar to a virtual circuit idea. We'll do an example here in a little bit. Routers may adjust or modify the labels because, of course, they have only local significance. At the egress point of the MPLS cloud, the last tag is what we call popped. It's removed, and then the only thing that's left is the original datagram. You can take separate pathways, right, and bind them together. So I got a label here and a label here. I can bind them together so that going forward, they have only one label. That means, or that handles the forwarding for both. The label creation, a lot of times it's done at the beginning, your topology is up and running, and then you implement a label distribution protocol, and that establishes the labels. It can be done on the fly, so when there's a demand-driven sort of approach, or request-based. We talked about integrated services in another video where you request services, and at that point you might actually request either a forward equivalence class change or an MPLS label to be implemented. Well, thanks very much for watching. Thanks for listening. This has been an introduction to the problems and ideas and some of the RFCs behind MPLS. Subscribe and like if I helped, and until next time, may your packets always reach their destinations.